Welcome, everyone. I will share my screen. Can you see my screen? Okay. Welcome to ACIGS Webinar Series, webinar number 51, with the benefits and potential pitfalls of leak location technology. We have here Simon Mann, Warren Hornsey, and James Mackenzie. Today's webinar is sponsored by FabTech. Few words about our organization. So we are Australasian chapter of International Geosynthetic Society, IGS. We have 46 chapters globally and representing 51 countries, which is pretty big organization. We would like everyone to join our organization. If you are a student, there is no fee and you will have discounted. And if you are a member as well, you will have discounted rates to our paid events. If you join us to the webinar library, you can see different webinars that we did in the past. Maybe something will interest you, and you can always go back to these webinars. This webinar will be uploaded probably within a week, so you can always go back to it. On our website, you can also find our events. So next event will be GINZ number 3. It will be held in Perth in July 2027. We are looking for sponsors. So if you are interested, please go to our website, ginzconference.com.au, and you will find different prospectus. Also, if you would like to upload an abstract, you can already do it. We also will have academic masterclass on geosynthetics, known as ETE, Educate the Educator. It will be held in November 2026 in Gold Coast. So if you are part of academic world, you can sign up by end of July. Here are our sponsors for the events. If you want to sponsor the event, please let us know. Our next webinar will be on 1st of July, and it will be Geosynthetics Installation Best Practice and ACIGS Role with Todd Harman, Brian Fraser, and Nick Morris. Thank you for all the company corporate members for supporting us. Without you, we wouldn't be here. So with a webinar, we will have first presentation from Warren Hornsey. He's Director of TRI Australasia. Then we will have Simon Mann, who is Managing Director of Liquid Integrity Systems, and James Mackenzie, Managing Director and Senior Principal at Mackenzie Environmental. At the end, we will have a little presentation from FabTech, who is a sponsor of our webinar. Please write your question in Q&A, and we will do it at the end of our webinar. If you need certificate of the attendance, please let us know. Okay. Now, off to Warren. I will share his presentation. Hello, Warren.
Hi, Alicia. Morning. Oh, afternoon, everyone. Okay, next slide, Alicia. So today, what I'm going to talk about are the available methods for the line integrity surveys, as in the methods that are set up by ASTM in carrying out these methods. I'll go into a little bit of detail on each one of them. In all reality, we could spend 2 days talking about these things and going into the full detail of it. So this is just a quick reference to the different methods. Next slide. There are two basic definitions. There are the bare membrane surveys and the covered geomembrane surveys. Bare membranes immediately after installation, they are easy to perform, but are extremely operator dependent. In other words, if your operator is rushing through the job, you may not pick up holes. It's real-time detection, so there's no data collection. You just find the holes. It can be affected by dirt and moisture, and it's very sensitive, very reliable. Covered geomembranes are extremely difficult to perform, and there are certain requirements in order to carry out a proper survey that needs to be sorted out before the project is constructed. It's no good coming afterwards and not having isolation and so on that'll affect the results. In terms of sensitivity, it's highly variable, and it really depends on site conditions, from cover materials to subgrade conductivity and so on. Next slide. Okay, in terms of bare membrane surveys, they're the water-based methods, ASTM 7007 with the water puddle method. It's a pretty fast way of doing the surveys. If you have a nice wide puddle, it's good for dirty surveys, wet and dirty survey areas, and it is more effective on wrinkles than the arc testing method is. The disadvantage of it is that you have to drag hoses around the whole site, and that can be a problem when you've got sandbags weighing down geomembranes. So you need not only the surveyor, but essentially 2 labourers to pull hoses and move hoses around. You can't do it on side slopes. As soon as you add water and work boots on side slopes, you start sliding down the slopes. It does require clean water. You can't just be pulling water out of ponds because it blocks the sprayers. And isolation is critical. Basically, if you have this water collecting in a sump that is earthed, as soon as the water trickles from the machine to the sump or the earth, the alarm goes off. So that's one of the disadvantages. Okay, next slide. The water lance method, this was probably one of the early methods of carrying out surveys, and it's essentially a very small area that you're surveying at one time. And it's good for pipe connections and seams, also very tolerant of wet and dirty survey areas. And it's certainly more effective on wrinkles and seams than the arc testing method. The problem is it's very slow because you've got this small concentrated area where you're spraying water on that's probably 5 to 10 millimeters diameter. And it's just not possible on side slopes. Again, slip hazards are a problem with that. All right, the next slide. If we go to the arc and spark methods that are out there, we do a lot of this testing on bare membranes because we can find really small holes and they're not limited by water flow through the holes. It can be done on slopes of 3 to 1, but really anything above that, you need to have working at heights certifications. And you can see on that image there, one of our technicians hanging off an abseiling rope, working on a large 1 and 2 slope. So it can be done. It is very slow if it's done properly. You can do it very quickly. You can walk very fast over a site, but you're unlikely to find all the holes because you need to move slowly in order to find the holes. It's extremely sensitive to moisture. So the survey area has to be dry and it has to be clean. It'll earth out against dirt and give you false positives in those areas. And you're unlikely to find holes and seams because the spark will only jump about 25 millimeters. The good thing is that if you do this survey, you essentially walk the whole site. So you do a visual inspection on the whole site. Okay, next slide. This is what is not acceptable with arc testing, is that you're not walking over the whole site. I mean, you can see the guys are not wanting to walk on a smooth slope. but they're not really pushing down the wrinkles. And these methods don't work on wrinkles because the spark only jumps 25 millimeters. As soon as you have a wrinkle that's above 25 millimeters, you won't find a hole in it. So essentially, the surveyor should be pushing down the wrinkles with their feet to make sure that there's intimate contact. Okay, so next slide. The next method is the covered dipole methods or covered geomembrane methods. And the first one is the water dipole. We normally do these with 100 volts going into the cell. They're very sensitive. They'll find holes and wrinkles. And with some of the equipment, we can do mapping on this. Not all of the equipment, but some of the equipment mapping can be carried out with this. One of the disadvantages are in terms of doing a water dipole with our equipment, and is that the water needs to be clean. We can't deal with high conductivity waters inside of there. You can't do it on sidewalls. So basically what we're doing is the floor of a pond, so we can't get to the sidewalls. And isolation is critical. Any earthed items such as steel or concrete that are earthing out, that can earth out the signal, will not allow the survey to carry on. And it's very slow. We're looking at 3,000 square meters a day. And if anybody's trying to walk through water that's knee deep, it's extremely tiring and very slow to do this sort of work. Next slide. The covered geomembranes, and this is kind of most of the work that we do is this type of work with after the gravel's been placed. We normally run the high voltage, 500 volts is normal. We control the amps, so the voltage doesn't kill you, the amps does, so we'll limit our amps to within safe working areas. But the advantage with these methods, if you use a large 3-meter double dipole, you can get up to 25,000 square meters a day. That reduces significantly if you use a single dipole. And voltage mapping allows external parties to verify the survey was carried out correctly. The problems with it is that moisture conditioning of that gravel is critical. If you don't have good moisture conditioning, you get lots of bad data, and then you can potentially miss holes. Isolation is critical. If you have large loss of voltage through poor connections to sidewalls and so on, you again will miss holes. And you won't always find holes and wrinkles with this method because the water won't necessarily run through the wrinkle and make contact with the ground underneath it. Okay, next slide. Now, this is an image of about as basic a dipole survey that you can do. There's no GPS tracking of locations. It's just a simple handheld voltmeter that somebody has to record the data as they walk along. Extremely slow and time consuming. And this went out of date probably 15 to 20 years ago. So just be aware, don't be using people that use these techniques these days. That is old technology. Okay, next slide. When you get the maps, this is the key part of it, is really understanding what you're getting. And what we're seeing in the marketplace is there's a lot of a tick and flick type attitude with this stuff, and we see mapping that doesn't really make any sense. And what you're seeing in the upper left-hand image is a survey where we can't see where the data was recorded. We see no contour maps, contours of what the voltage readings are. And that's part of the standard. And it requires you to show the contours and so on. It also requires you to show where you've recorded the data. So if the second image over to the right, you can see that the survey was carried out, but there were large areas where no data was recorded. And that really is not acceptable from a standard point of view. So anybody that's getting in a report should be looking at both the contours and where the data is recorded. And the image to the far right shows a good survey with regular recording values where you can clearly see the artificial leak in the top left-hand corner of the survey and the current injector in the center of the cell. Now, the devil is in the detail with all of this stuff, and the standard allows you to play with the voltage contours that you see because every site is slightly different. But really what you can do is go along, and if you put a very wide contour a gap on your survey, you can hide holes or miss holes. And depending on the site, you may have to have a very close contour spacing to really be able to see the holes and investigate the anomalies correctly. So it's something that you really should be looking for somebody that's getting a report like this. Okay, next slide. The issue is that it's extremely hard to verify that a survey has been carried out to acceptable standards. But to give you an idea, we've been keeping a track of our jobs since 2018. And we've done 106 sites, 1.7 million square meters. And on average, we see 0.78 hectares holes per hectare, which is less than what Giro and so on initially indicated as 2 holes per hectare. But what we're seeing is with good CQA, the quality of the landfill bills are becoming better over time. Next slide. So the way to double check this that I would recommend for everybody is to put blind holes into their cells if they're building these cells. There is a standard on how it should be done. And that way, if you go out and do a survey, if your surveyor can't find your holes, then there's a problem either with your survey or the sensitivity of the site. And one way or another, you have to fix that to be able to verify that the survey or that the cell has been built without any holes in it. Now, lots of people don't like putting holes in a perfectly good geomembrane. And the only alternative to this is, and if you go to the next slide, is to put an artificial blind hole in. In other words, just run a wire, place it between the geomembrane and the covered protection geotextile, and have that as an artificial blind hole that people can find. The problem with that is it doesn't really confirm that the subgrade conditions are acceptable, but it gives an indication of whether the person's equipment is working correctly or not. So I would be recommending that everybody put some form of blind holes, whether it's a real blind hole or an artificial blind hole, into any one of their projects before they go ahead, so that you can verify that the survey has been done correctly. It's the only way that you can really verify that your survey has been done correctly. And that's the end of my presentation. Thank you.
Thank you, Warren. And we will go to Simon next.
Thank you, Alicia. All right, can my screen be seen?
It's loading. Yes.
Fantastic. Welcome, everybody, and thanks for joining us. Thank you to IGS and thank you to FabTech for sponsoring this. It's going to be tough to squeeze everything I would like to say into 15 minutes. Like Warren, it takes, there's a lot to talk about here. So I'm Managing Director of LIS. We specialise in surveying deeply filled lagoons, and some of the challenges that Warren talked about just now, I'll discuss in a little bit more detail as well. So just as a little bit of very quick background, what we're really looking for in electrical leak detection is current flow through an insulating liner. So if we look at this left-hand panel here, we can see current flow. This is a modeled result. This is the current flow through an insulating liner. And in almost all scenarios, we're looking to gather data in this overlying conductive medium, whether that be soil or whether that be water. And we're using our electrodes and our dipole to measure the change in electric field as we pass over this leak. The right-hand plot you can see here shows what it is that a technician or an interpreter is looking for when they're trying to find a leak. So this is the classic dipole type signature. that we might all be looking for. If you're running 7007 standard, then an operator might be looking for this live. If you're using the latest 8265, then we're looking for this in a map, as Warren showed, and I'll show some maps as well. So this is really what we're looking for. And as you might expect, as we go deeper and our sensing platform is further from the leak itself, our signal changes. So if we're talking about deeply filled lagoons and we're measuring from the surface, which is what I'm talking about, or if you're measuring from the top of a landfill cap or something like that, then you're measuring well above the leak, and that signal will be smaller and potentially changed as a result. So just as a bit of background, generally practitioners will be applying anything from 20 to 40 volts. That's typically what LAS use. And I should preface most of this conversation, this presentation, with the fact that there's very little technical detail on what other companies are doing publicly available. So a lot of what I talk about today will be our experience and our knowledge. So we would tend to operate in the 20 to 40 volts type range. But as Warren talked about, typically you'd be in the hundreds of volts, and anecdotally I've heard some operators in the thousands of volts. We're sensitive to damage beneath the conductive medium we're surveying in, so that's below the soil, or that's at the waterline or below the waterline, and it's appropriate for operational sites with the testing liner under operational loads, and we do work in single or double liner sites. Why are we testing fill ponds? If they're built properly, if they're constructed properly, if they're used properly, then leaks really shouldn't be an issue. But typically our clients have one of a small set of problems. Either they know they have a problem, they suspect they have a problem through indirect means, they can't afford to have a problem, i.e. it's a high-risk site, or they need to show that they don't have a problem to meet their license obligations. The benefits of doing this would be that it's operationally convenient, less damaging to the lining system to survey it while it's covered than to empty it and potentially damage it further. It may be your only option if you don't have anywhere to put your waste or water. It allows a targeted repair. So if you have a survey done that tells you there's a leak in a particular area, you don't need to empty the entire site potentially or clean the entire site to access that. And it may be more appropriate to test under an operational load. And Warren touched on this as well. If you've got a wrinkle or you're depending on what your dry liner methods are, you may not be sensitive to all leaks. So that QC process may not pick up everything. So in terms of where this technology is best used, I thought we'd talk about who uses us, because that's what we know. This site here is a site near Adelaide. It's a small fruit producer in an ecologically sensitive area. He needs to meet his license obligations, and that is to assure the EPA that his site is being monitored and doesn't leak. Typically, and before he found us, his approach would have been to get a crane in to lift out this aerator, remove a walkway, empty the pond, which stops his operations, by the way, and clean it and have dry liner methods used. Obviously very expensive and very disruptive to his small business. In this image here, you'll see our little boat. You'll see that a few times in this presentation. We turn up and we do this job in half a day. And out of interest, we have found leaks in his site and have helped him towards a leak-free site. We have big industrial sites that we visit. So both of these sites that you can see here are from North America. This client knows they have a leak in a brine pond because there's a leakage sump. It's a double liner system. This client knows they have issues because it's a high risk site. And they also carry out regular dredging activities, which means there's a potential for further damage. So we'll see some data from a similar site to this in a moment. But these are the kind of people that know they have problems and will call us in. In that same vein, here we've got an example of a brand new site. This is a huge tank here in Australia, 17 megalitre tank that on commissioning and first fill did leak. Again, we know there's a problem. This is a double line site at a metal processing plant here in Australia again. Again, a double line system. So we're there because the client knows they have a problem. This photograph on the bottom right sort of highlights some of the difficulties in doing autonomous or remotely operated leak detection surveying. These sites commonly have lots of baffle curtains, tethers, pumps, all sorts of infrastructure that can get in the way. We turn up on sites with suspected problems. So both of these sites here, this is a metal processing plant in Australia. On the right-hand side, we've got a dairy site in the US. Both of these sites suspected they had problems because of groundwater monitoring nearby. So they don't know, they hope they don't, but they suspect that they do. So we're there for that reason as well. And we also get involved in commissioning new ponds. Where's that? Here on the left is that tank that we saw before. On the right is a brine pond here in Australia that's just 10 metres deep. This is the pond where we've detected our deepest leaks at over 10 metres in brine. And again, you'll see our little boat moving around. The centre image here is us testing an underground tank with a submersible. And again, and to tie in with Warren's comments, this is a brand new liner in this tank. It had been spark tested and the problem could not be found, but it was known to be leaking. So how would you tackle this traditionally? We would commonly be doing what Warren was talking about, and that would be carrying out a wading survey. As he says, there are issues with that. And primarily you've got land-based equipment being used in a water context, and the operator needs to be in safe operating depth. So we're looking at 3 to 4 feet to work in. A lot of ponds have sloping floors, which means that if you want to survey the whole site, then you need to be changing the level during the survey. So relatively slow. There are drag probes. There are companies offering drag probe surveys, and this is effectively dragging those sensors across the bottom of the pond using ropes and or cables at the side of the pond. This can be effective. It's physically demanding, it has high labour requirements, and it has relatively poor accuracy depending on the site, location accuracy that is, depending on the site and the weather conditions and all the sort of things that you might have problems with dragging cables across a pond. People have attempted to put land-based equipment on floating platforms and move those around on the surface of a pond as well. Or you have the old option of emptying and cleaning the site and then applying dry liner methods as Warren described. So in the last 5 years, USV or unmanned surface vessel technology has come a long way, and this is partly what we specialise in. We're not the only company that does this. There's very few others, and as I mentioned, there's not a lot of information on what else is available. So what I say here reflects our experience and our knowledge. These are small vessels which basically have data logging systems on board, and to meet the new standard, we've also got highly accurate GPS as well. So that our boat is maybe 1 metre in size and is easily deployed into the pond without a person going into it. We've worked in ponds over 10 metres deep. There's not that many industrial sites deeper than that, but that's the deepest we've detected leaks in, and anything deep enough for the boat to sail in, basically. You do not require technicians to enter the site. It can be carried out while the ponds are in service within reason. It offers a chance to test the liners under operational conditions, and it allows management of issues without having to drain the site. As I said before, if you know where your leaks are, then you can start to come up with a plan without having to affect your operations. To carry out in dangerous environments, we've worked in brines many times, seawater concentration, caustic brines, and we've worked in acids as well. So the boat will go into more or less any liquid, and we're not hindered by those sort of conductivity issues that Warren spoke about. And it allows a cost-effective, proactive approach to asset management. There are challenges, though. It can be very difficult to do what we're doing. I think most commonly the signal strength, and I'll present a little bit about that now. The signals we're looking for in deeply filled lagoons would be 1,000 to 10,000 times smaller than they would be in a soil ELL survey. So really the recording system needs to be able to remove and filter unwanted signals such as electrode offsets, telluric noise, electrochemical signals. These alone can be more than 10 times the signal you're really looking for if you're looking to pin down multiple leaks in a deep site. Current soil covered equipment, as far as I can see, is not equipped to do this and is not suitable for simply sticking onto a floating platform. There are obstacles in the water. So there are 2 photographs here that clearly show the sort of things that we work around. We've got a large aerator here on the right. On the left, we've got a site with 16 aerators. Not easy, but just the logistics of data collection in these environments can be challenging. There's a lot of grounded infrastructure in these sites. It's not possible to excavate a trench like it might be with a soil covered. So isolation is a real issue, as it is for all leak detection methods. We can work in conductive liquids. If you're playing in the space where you're looking at microvolts to millivolts to look for signal strength, then you're also sensitive to changes in bottom topography. So, for example, a bund being present at the bottom of your pond will concentrate current above it and may generate a signature that looks like a leak. So we need to start to think about things that aren't common in other ELL applications. And we have to think about the implications of false positives as well. The cost of any of our clients to excavate or empty a site and clean, looking for damage if it's not there, is high. So this needs to be a service that's carried out to as high a standard as possible. A lot of this is done in digital processing, and as Warren talked about a little bit as well, 8265 requires the provision of a geo-referenced data set that somebody else could interpret. And just to talk about the signal strength issues, on the right-hand two panels here, we can see two plots for two of our surveys. The one in the middle, the black and white one, it's a 10 hectare site, and you could see, as a layman, any of you will probably be able to start looking and seeing leaks on this plot. On the right-hand side, we've got a similar plot from a 5 hectare site that's presented slightly differently and has the anomalies marked on them. On the left-hand panel, we can see a plot that TRI have been nice enough to let me share. This is a typical soil-covered site, and as Warren talked about, there's different ways of playing with those contour levels. And as far as I'm aware, TRI offer the high standard soil-covered surveys, and they're plotting the data to 0.1 of a volt. The data, if you look at the plots that I've presented here, the data that we're looking at here on the right-hand plot is 1 millivolt. The one in the middle is 1/3 of a millivolt. So the full range of data that we collect in our surveys would fit 100 times into a single contour on a soil survey map. So the difference in magnitude is huge, and we need to be looking at these very, very small signals in order to see leaks in deep water. There's other things. The standard, for example, requires operators to keep a fixed orientation for a dipole. A dipole being 10 degrees out from where it should be will produce a different signal. So little things like that can definitely creep up, and typically there's a much stronger than the signals we're looking for. And just to put it in a slightly different context, here is the plot that I showed before of a real leak on a site that we've detected. On the right is that same leak presented to a 0.1 data range, and it's very difficult either for an operator live or for someone in processing or review to detect that leak. We need to maximize the current flow through every leak. So it's really important to plan your site and plan your survey properly. And as Warren explained, going right back to the design of the pond is also really key here. We often don't have the opportunity to isolate and then retest like you might do with soil surveys. So for example, in a soil survey, you might take a big leak and excavate it and isolate it so that you can carry on the survey and hope to see subsequent leaks. We don't have that opportunity with deep water surveys, so we need to be able to see multiple leaks at once. If isolation issues can't be removed or reduced, then some assessment of blind spots should be reported. Isolation is commonly the largest issue to quality deep water surveying we have, and we really look to our clients to help us with drawings, photos, planning. It's really usual for us to turn up on the site and be surprised by something that's there. So this is where the client can really help with a quality survey. And technicians need to be very observant. If we don't get full isolation of a site, electrical isolation, then we can have issues, and this affects all leak detection surveying. LIS has developed a method we call current shielding, which reduces the effects of poor isolation for infrastructure. This is not a panacea, so we're not going to suggest in any case that we shouldn't be looking for complete isolation. That is best practice. If that can't be done, we can apply current shielding. The bottom two panels here show a before and after current shielding scenario. On the left, we've got a conventional ELL setup where we've dropped a current injector into a site. And we have four, hopefully you can see them there, four very well-grounded pipes entering this thing. And what we're generating there is a very strong field within the site that swamps our leak signatures. By applying current shielding, we can reduce this substantially, and those leak signatures start to pop out. On the top right, that plot there is a real example of a site that we surveyed. This is the same leak on the same day. In the left-hand panel in the top, this is your conventional ELL setup, and there's really no response due to that leak as a red dot. On the right-hand side, we've got a current shield example where there's a very clear dipole response from a leak. So there are things that you can do if isolation is poor. Survey speeds, typically when the boat is on the water, will cover over a hectare per hour. So it's over 10,000 square meters per hour. But the boat being on the water is just a small part of the total surveying, from the setup of all the equipment to the data review, to surveying this area more than once. We would commonly survey a site at least twice completely to give us 2 independent data sets or even more. So on average, we would work to about 2 hectares per day. So this is on the upper end of what you would achieve with a person or manual surveying. So similar productivity. But the data density is way, way higher. So we would be collecting data every couple of centimeters. A manual method might be every couple of meters, for example. With autonomous vehicles, we don't have fatigue issues. So it's easy to get more data. And I would always argue more data, more data, more data. If you combine a USB with the latest standards, then you've got a really powerful, really useful tool. Now we'll look at some examples. So the top here is a plot of some data we've collected in North America. This is a site that we visit regularly because this site is prone to ongoing damage and it's a sensitive environment. The red dots here are anomalies that we've identified in this year's data. The white dots are anomalies that were identified in previous year's data. So what we can see from this plot alone is that A, there's been successful repair of multiple leaks. B, some of these leaks have not been successfully repaired. So that's a question for the lining contractors and the repair crew to understand why they haven't repaired it properly or what risks there might be in that. If we look at the bottom left panel here, there's an aerial shot showing this anomaly that's in the bottom left here, and it's associated with a pipe over the crest. Now, we see this quite a lot. We see a lot of damage due to operations. So we start to help the client understand where the damage is coming from. Similarly, on the right-hand side of the bottom right panel, we've got a very strong leak anomaly associated with a very large over the crest pipe. In this instance, the client was looking to ignore this signature because they felt it was the pipe causing this signature. Because our technicians were observant on site, we could say we looked at this pipe. This pipe's purely HDPE. It should not produce a signature like this. And they did go and inspect this area, and they found a 2-foot gash that this pipe had put into the liner. So again, ELL or ELL done properly can guide better site operations. So what have we learned? Leaks can occur in a pond due to any of 3 stages. So we've got the design, and I guess there are others who are far more expert at designing ponds than we would be, but you've got things like poor drainage or a lack of spillways, improper subgrade, underliner drainage systems that don't work very well. These might contribute to damage to the liner. You've got construction, low quality installation, poor weather while it's being laid, unsuccessful welds, all these kind of things can lead to leaks. Or you've got operations, and this is what we see a lot. This might be over the crest pipes, ponds left dry, animals trapped in these sites can cause damage as well. Our boat is equipped with sonar as well. And if we look at this top image here, we've got a side scan sonar image of the bottom of a pond we've been surveying. And if you're not used to looking at these are a bit like a grainy black and white aerial photograph. So we're looking down on the lining system here, and we can see whales developing, or bubbles in the liner developing under this pond as we're surveying it. You can see the tension and the wrinkles that these whales are causing on the liner. This is not something that a liner is designed to cope with, and it's going to lead to failure at some point. And further advancements, I need to mention our submersible technology. This works in the same way as all the rest of it, but you can put it into covered storages. It works down close to the liner. We've used it in verifying repairs. So we might have a dive team go in and make repairs. The ROV can fly over it and confirm repairs and things like that. So this is the latest development in the ELL. And that was it. So thank you.
Thank you, Simon. And now we have James Mackenzie's presentation. I will share that. Can you see it?
Yes. Thanks, Alicia. Okay, so we've had some IT issues, which is not, it's not new territory for me. So Alicia is running my slides, and I thought I was very smart in doing quite an interactive slide, but let's just see how we go, Alicia. So I'm going to talk about leak detection as part of of a CQA plan and where it fits in, and talk about this more holistically. So if we go, Alicia, so quickly about me. So I'm a designer of containment systems, largely in landfill applications for landfill caps and baseliners. I also have a history of undertaking CQA inspection. It's what I did as a graduate. And my company, Mackenzie Environmental, routinely provides those services, again, in the largely in the landfill space in Victoria. And I'm definitely not the leak detection survey expert. I think we've just heard from two of them. So I'm throwing in a different angle. Thanks, Alicia. So understanding leak detection surveys. Yep, let's go. So from a designer and asset owner perspective, so do we need a leak detection survey? I would say yes, definitely. And then now it's pretty much in the industry that I work in, standard practice. And if so, which one is appropriate? So both, and as a designer, you need to understand that when you're specifying it, so that come construction time, it all runs smoothly. Can a leak detection survey replace full-time supervision? Well, I mean, it can, but I would suggest it doesn't. And we'll get to why and some examples of that later on. When do we do the survey? So for my designs, we specify the survey to occur after we've placed the leachate collection aggregate in the floor of the cell. So on the dipole testing that Warren was saying that his company does a lot of, that's the experience that I have with leak detection surveys. Who do we get to do it? Well, we've just heard from two people who you could probably call, and there are others. And how many surveys do I need? So as I say, I specify the one survey at the end of the works after the leachate collection aggregate's gone down. We often get asked, well, why wouldn't you survey it before that? Well, we're pretty comfortable before that with full-time supervision, that there's not too much concern. And the survey is largely to provide confidence that the processes to place the aggregate on the liner hasn't led to damage. Thanks, Alicia. So how do we minimise holes and get the best possible liner installed? Because that's what we're on about. Next. So no, we don't just specify leak detection survey. In fact, I'd say not even close. Keep going. Thanks, Alicia. So you need to start with a robust design. Without a well-designed liner, you're in trouble. And when I say well-designed liner, I mean the design is the entire package that is specified. So that includes specifying how the cell is to be, or how it's to be built, with what plan, what are the restrictions. So, specifying trial pads, ensuring that you've done some compression testing if you're putting aggregate over the liner system and so forth. Secondly, you need to engage an experienced installer. So there's only so much a good design and some good CQA can do. And so definitely an experienced installer is certainly part of the package. And thirdly, a robust quality assurance program. So typically we have full-time inspection and testing services during construction. And then the leak detection survey comes at the end, but in my opinion, it's got the least impact on the final outcome. Next. Thanks, Alicia. Yeah, so I'd say think of it as an audit, financial audit. If you've been doing everything correctly, ticking all the boxes, you've engaged the right accountants, you've paid your taxes, you've probably got little to worry about. But if you've been cutting corners, you'll probably be found out. Thanks, Alicia. And so now we'll go to some case studies. One's a good news story and one's an example of, I guess, what I am saying here. So Victorian landfill circuit 2007-2008. So there was issues with design, and when I say there was issues, I won't go into it greatly, but the design was lacking in nearly all the processes now that would be part of a design in a landfill in Australia. There was no CQA requirement during the aggregate spreading. There was no need to conduct a trial pad. The design didn't include compression testing. And so subsequently, the auditor required a leak detection survey to provide himself some confidence that this liner was installed as intended and would perform as intended, because there was some concern. The subsequent leak detection survey, and it might have been the first one in Victoria on a landfill liner, it found an estimated 1,000 holes. The survey stopped. When extrapolated out, the story had been told, and that photo there is of the liner, and all the little spray painted circles are the defects, and they were nearly all from the aggregate placement. The liner was removed and a new liner installed, and I think at a cost in the end of around $1 million, and obviously significant delay to this landfill cell being ready to receive waste. Thanks, Alicia. There was a paper written on this, and it said that appropriately prepared plans had been put in place, and the case study clearly demonstrates that despite having appropriately prepared design documents, the geomembrane liners can still be damaged. Next, Alicia. Yeah, so I would say sort of. The design was lacking, the supervision requirement, which comes out of the design, was lacking, and what the leak detection survey had to say was indicative of what had gone before it. On the flip side, the Wollert landfill in the northern suburbs of Melbourne, it was one of the first sites, or I think it was one of the first landfill sites to have leak detection survey, and that came about by the manager of the site at the time, Sam Bateman. He decided he wanted it, which was probably a little unusual, and he was ahead of EPA Victoria before they mandated it. And I think the first cell that had a leak detection survey is a couple of, he got them from Eastern Europe to come out and survey the first cell, and it's probably had more than 10 cells now subject to leak detection surveys. It's always had good design. I might be a bit biased there, but it's had robust CQA. It's always had trial pads conducted, and typically, and I haven't gone and researched this, but from memory, the surveys have found just in the order of 2 to 4 holes per sort of 3 hectare cell. So that's a good news story, and that's what you want your leak detection survey to be telling you at the end, that everything that went ahead of it got the right outcome. Thanks, Alicia. So in closing, leak detection surveys, they form part of a complete CQA package, absolutely. It's an add-on to full-time supervision, and with quality design, an experienced installer and good robust CQA, you'll get a good news story from it. But with a poor design and a lack of suitable CQA, and if you want to throw in an inexperienced installer, maybe brace yourself. And what's our aim really at the end? For the leak detection survey to confirm that all that came before it was appropriate. Thank you.
Thank you, James. I was wondering who was installing the other one in 2007. We will go to FabTech now. So it will be just 5 minutes presentation. They have some case study, and after that we'll do QA. Please share your questions. We don't have that many today, so yeah, I encourage you to do it. After you, Graham.
Thank you, Alicia. Just wanted to share a couple of case studies showing the use of the emerging high capability technology. The first one relates to a leaking asset, 5 hectares, 4.5 meters deep, could not be taken offline, had whales, and you can see on the top right that whale is about 4 meters in diameter at the surface, causing huge load on the geomembrane. The whale was being fed by gas from leaks and then decomposing organics. It was a regulated site, and so the work needed to be done to satisfy the regulator that the construction repairs were done to an appropriate standard and then verified to be so, and that was by repeat surveying, as Simon interestingly mentioned in the example in America. So we had to work in toxic deep water. Because of that, there were 2 fundamental requirements of the leak location system. One was it had to be capable of measuring microscale defects, which conventional technology couldn't do. And the other was that it had to be really accurate in terms of location. We couldn't be sending divers into toxic liquid that you can barely see anything at all in any way, and have to try and find where the defect was. They had to be able to find exactly, very precisely, to just a few centimeters where the defect was. Again, impossible with conventional technology. And from a safety point of view, using an unmanned survey vehicle obviously avoided people dealing with that nasty environment, improved safety, and was much quicker than alternatives. So what we did was to initially to deflate the whales. The whales prevented surveying those features, and indeed when we then commenced the survey, with the sonar found quite a few submerged whales that hadn't yet surfaced, which was interesting. The survey environment for this technology was actually not overly complicated. The liquids were okay to map in, not too deep, 4.5 meters, so the survey was relatively predictable and trouble-free, which is great for emerging technology. The repairs were more troubling. We had to undertake VOC processes to satisfy the regulator that we could perform suitable repairs, and then the acid test was performing the post-repair survey to confirm that the leaks had been fixed, and that's what occurred. In actual fact, every leak have been successfully repaired. Would not have been possible to undertake any of that work other than to empty the pond alternatively. Second really quick case study is about commissioning best practice. The example here is a high value asset. You wouldn't do this on low value assets, but a high value asset, a potable water system. It's aligned and covered storage. It's much more complicated now because before water goes into the asset, the flooding cover is installed, and then you're denied access to the lining system. What this technology allows us to do, so initially we usual normal construction quality control procedures, overlay on top of that with the electronic arc testing to make sure the barrier system, the liner, is to the highest standard through conventional techniques. And then we traffic all over the lining system, installing a floating cover, which is obviously a risk. And as you're deploying the cover, you're then concealing any problems that you might have created. So apart from using processes based on experience, there's a risk that there's some kind of damage to the lining system. So post completion of the whole asset, best practice for us is to have a wet commissioning process, put full hydrostatic load onto the system, and then inspect. In this particular case, the lining system was a primary liner, a conductive medium. The liner was not conductive, a conductive medium, a drainage system, and a secondary line. The survey platform was an underwater drone. The drone's been developed so that it fits through a conventional diver's hatch. Most assets like this, floating cover assets, have a diver's hatch, so that's really a key requirement, so that you can replace the diver with the drone. And the drone is equipped with leak detection capability, cameras, and sonar. Not that we need sonar in this particular case. And then in terms of inspecting, so on top of all the conventional work that we've done, some defects, actually particularly cuts, can seal at no or low hydrostatic head, but at full hydro head, we open up these defects and we're able to find these defects. The leak location component is really accurate because the drone obviously flies along close to the surface of the geomembrane. So while the technology is able to do deep water survey, we don't need to. It can fly really close to the geomembrane. In these structures, typically, in these assets, typically, there are little outlet structures. There's concrete and a few things that you can't eliminate. And Simon mentioned techniques to help survey close to these features and still get good quality signals. Another really useful benefit, not uncommonly, the drainage system is not totally sealed, so there is some element of groundwater getting into the drainage system underneath the liner, and so you can obviously measure the flows, if any, and the water chemistry, and try and guess at seepage rates. This gives a third element to better quantify and have confidence in the level of measured seepage rate. And another really important feature is that you can see the lining system under proper load. So wrinkles and features such as that when you're walking an empty basin look really different when you subject the asset to these full hydrostatic loads. Obviously, safety, there's a huge benefit not putting divers in. Divers are pretty reliable, but the first step in safety is to eliminate the risk, and far better not put a diver in than put an experienced diver, with a good safety record. And we have used this technology in areas where there's flowing water, where you wouldn't allow a diver nearby, and in areas where there are high risk locations within the asset, which again you wouldn't let the diver near, but we're able to put this technology in. So the outcomes of these kind of studies, which we now do on most potable water assets, it's a quick commissioning process. If there are defects, they can be fixed. And really importantly, these assets with a life of 30 plus years, typically 30 to 40 years before recycling the geomembrane materials, replacing them, you've got this excellent fingerprint of the as-built condition that each subsequent annual or biannual inspection can compare with. You're not looking at a picture frame of a video in isolation. You know exactly what happened before. So there's really quickly, I could go on for a while, but there's really quickly just two examples of utilizing these technology advancements.
Thanks, Graham. Yeah, and I just want to follow on from what James was saying about a systems approach to getting good outcomes. We try to get our designers to think in terms of a lining system as opposed to a geomembrane, because it's a different thing. Thinking about the subgrade, thinking about the low permeability layer, thinking about the geomembrane protection, drainage. It's that system that works. It's not just one part of it. So getting that thinking into how we install the geomembrane makes a lot of sense. Got two questions, both asking about conductive geomembranes and where those fit into this process. I wonder who best would be able to comment on that, because I think what we've covered mostly today was a standard non-conductive geomembrane.
Well, I can answer from my perspective. From my perspective, from a purely liner integrity survey point of view, it would be great if every geomembrane was a conductive geomembrane. But that has economic consequences. But from a survey perspective, it would be great if all of them were conductive.
Yes, I would agree. Any time a conductive membrane is used, I guess as ELL practitioners, we've got more confidence that more of the current we're applying to the site is going through that leak rather than being lost in soil. So yeah, I think it's a useful tool, absolutely, for helping successful ELL.
Great, thank you. And then another question, could you comment on what strategies can be taken for leak detection in facilities with high conductivity materials being stored in them? I did hear that that is doable with some of the surveys that you are using now. Just if you can expand on how that works a bit.
Yeah, I think the ability to survey in conductive liquids is not a limitation on the method or the principle of how this whole thing works. It's a limitation on equipment. Our gear has been designed to apply sufficient current so that we can survey in these areas. But really, there's no practical or no, in principle, limitation to surveying conductivities. As I said, we've gone from brine ponds, lithium brine ponds to fresh, and it makes really no difference in terms of the signal that a leak produces. You've just got to have the equipment that can energize a site suitably.
Then we got a question here about a 2 meter deep, sounds like a sump, concrete sump covered with a bituminous liner from the inside to prevent water and gas ingress. What method would be best to use on that? Yeah, I'm not sure how BGMs respond to electrical leak location surveys. I think we've been speaking about mainly non-conductive geomembranes, and I guess the fact that I'm not sure whether a BGM is conductive or not.
Laura, I'll let you comment if you, yeah.
Look, BGMs, you can carry out surveys on BGMs. They're isolated insulators, so they can be carried out on BGMs. So, and we have done surveys on BGMs. In terms of the question that you're asking, I'm not sure what the answer. We'd have to have a look at that in a little bit more detail in terms of exactly what they're trying to achieve there. It's difficult to comment on that.
Because you've got the concrete in the mix as well, which I think does change things.
Yeah.
Great. Oh, that's the end of our questions. Just want to say thanks to all our presenters and to our sponsor. I think it's again just an illustration of how useful these techniques are and how they form a vital part of quality assurance and making sure that any geomembrane sealing system installed does its job. So yeah, thanks everyone.
Thank you, everyone.
Thanks, Seb.
Thank you all.
Thanks, guys.